This unit will help you understand elements, compounds and mixtures and their differences. And the last section will look at the separation techniques you need to know for your test. So we'll start with elements. All materials, everything around us, are made up of chemicals and can be classified as either living or non-living, ranging from complex structures like ourselves and this plant to what look like simpler things like paper and plastic. Everything is made up of chemicals, and for your test you need to know about different types of chemicals and some of their properties.
Chemicals aren't just things you find in labs. Everything around you is made up of chemicals. This cake is made from all these ingredients.
But what are the ingredients made out of? They're all made out of chemicals called elements. Elements are the building blocks of everything around us.
This lot certainly don't look very tasty. In fact, some of these elements are toxic and dangerous.
So, what's special about elements? They're pure substances that cannot be split up into simpler substances. All elements are made up of tiny particles called atoms, and each element is only made up of one type of atom. Elements can be represented by a symbol, and you've probably heard of some of the most common ones. N for nitrogen, O for oxygen, Fe for iron, Hg for mercury, S for sulfur, Cu for copper, and C for carbon. At room temperature, elements can be solid, liquid or gas, so that the elements nitrogen and oxygen, gases, look very different from the elements copper and carbon, solids. So you need to know that elements are pure substances and are only ever made up of one type of particle, called atoms. We see very few pure elements in everyday life. Here's mercury in a thermometer, silver and gold jewellery, and helium gas is used to fill balloons. Elements are rarely seen because they're so often combined in chemical reactions to form compounds. Watch what happens when we combine the two elements sodium and chlorine gas.
Elements are made up of tiny particles, too small to see with the naked eye. Particles of one element are all the same. Imagine these are particles of the element sodium. Chlorine particles are very different from sodium particles. But when particles of different elements get together, two things can happen. They can be mixed together, but they keep their own characteristics and are easily separated. Or they can join together chemically. They're much harder to separate now. The chemical combination is called a compound.
So a compound is a substance where two or more elements have joined together chemically, and the combinations of elements within these compounds are always in fixed proportions. Mixtures are made up of particles of substances which have not been joined together in a chemical reaction. Here is a mixture of sulfur and iron. They have not reacted chemically and can be separated easily. The iron is magnetic and can be easily collected up with a magnet. My cup of tea is obviously a mixture. It has several ingredients. But how about the ingredients themselves? Here's a question for you. Are each of these, milk, sugar and water in my tea, mixtures or compounds? Why not stop the tape and have a think? So, which of these three examples are mixtures and which are compounds? The answer is only the sugar is a compound. it only contains one substance. Remember, in a compound, the particles are combined chemically and they are all the same. Milk is a mixture of fat and water, minerals and vitamins, and ordinary tap water, well, it looks pure enough, but it is in fact a mixture. There are other things in it. In this next clip, Femi goes under the Derbyshire Hills and takes a closer look at the local water supply there.
Stalactites are formed by dripping water over thousands of years. The drip of water dries up and leaves behind tiny crystals of calcium carbonate.
Calcium carbonate, a compound. Ah, so already we know that the local water must contain calcium.
And the band of orange on the wall indicates that there's iron in the water that's passed over this area.
So that could be in the water too?
Correct.
Alan showed me examples of other substances like manganese left behind by the water. It looks like there could be much more than just the elements hydrogen and oxygen in the local water.
This is the lab where the local water is tested, and Karen here does the testing. Can you help me out here? I'm a little bit confused. The locals call this water pure, the leaflets call this water pure, even the bottle claims it's pure, and yet it looks likely that it does actually contain calcium, iron and manganese.
Yes, you're right to be confused. That's because the everyday use of the word pure is somewhat very different to the scientific use of the word pure. This sample of water is actually a mixture of water and all of those minerals that you mentioned earlier. Pure water contains entirely the elements hydrogen and oxygen.
So where can I find pure water then? Scientifically pure, I mean.
Well, if we take this sample of water for starters, I'll show you what we can do.
Karen heats up the mineral water till it starts to boil. The minerals in the water can't boil off, but the pure water can. The pure water vapour passes up through this tube. The tube is kept very cool, so the water vapour condenses and water trickles out the end. Scientifically pure water. But when all the water's boiled away, what's left in the flask? You can clearly see traces of minerals left behind on the side of the flask.
So scientifically, the mineral water is no more pure than my fizzy drinks.
Indeed, they're mixtures too.
But that is pure water.
Yes, this is pure water. It's actually tasteless, and it's the minerals that give the water its unique taste.
I think I'll stick to the natural, but not scientifically pure, Buxton water. Cheers.
So when referring to the word pure in chemistry, pure means a substance which contains only one type of particle. Mixtures are a combination of substances that are not chemically combined and can be separated. So ordinary water that we drink and use for everyday purposes is in fact a mixture of water and minerals that are dissolved in it. We can get pure water with nothing else in it by distillation, but that's in the next section that we're going to look at. In chemistry, mixtures often need to be separated, and in the next section we're going to look at the separation techniques. There are 5 different separation techniques you need to know for your test, and also when you would need to use each one. In this next clip, several different separation techniques are used to separate salt out from rock salt. Try writing down all the ones you see.
It's the only rock salt mine in the UK, and it's enormous. Hi, George. Yeah, I've collected my rock salt sample for analysis, so what do I need to do?
Well done, Trish. I've put the rock salt nicely on the weighing paper.
Lovely jubbly. Take 100 grams of fresh crushed rock salt. Add water and mix well for 2.5 hours. The salt dissolves, but of course the clay does not. Pour the mixture through a filter. The clear salt solution passes straight through into the flask. But the brown clay particles are too big to get through the filter paper. Heat the salt solution. The water evaporates, but the salt is left behind. By subtracting the weight of an identical empty beaker from the weight of my salty one, I can calculate I have 94.8 grams of salt.
So, what separation techniques did you come up with? You should have come up with two separation processes. The clay and salt were first separated by filtration, and secondly, evaporation. The salt solution was heated, the water turned to water vapour, and the solid salt left behind. But if you had a salt solution, and this time you wanted to keep the liquid and not the solid, the salt, then the separation process needed is different.
You may wish to separate a solution of salt water and keep the water. In this case, the solution is heated in the same way, but the water vapour, or steam, is trapped and channeled into another container where it cools and returns to liquid. Separating a solution in this way is called distillation.
So filtration is used to separate a solid from a liquid. Evaporation is used when you want to separate a soluble solid from a liquid when collecting the solid. Distillation is used when you want to separate a soluble solid from a liquid, but this time you want to keep the liquid. When a mixture of liquids needs to be separated out, for example this crude oil, a process called fractional distillation is used. The different liquids have different boiling points, and as the temperature of the crude oil rises, each liquid in turn reaches its boiling point, vaporizes, and then condenses back again into the liquid. Fractional distillation is used when a mixture of liquids with different boiling points needs to be separated out and collected in large quantities, like the example we just saw, crude oil. But what happens if our liquid comes in very small amounts? Ink is made up of several different pigments, and to separate these colours out, an entirely different process is needed.
Ink is a mixture of coloured dyes dissolved in water. The mixture, or solution, can be separated to show which colours it contains. It's then possible to find out what kind of ink was used. The writing on this piece of card looks as though it was drawn with one kind of black ink. We can test this by taking a sample of the ink used for each letter and placing it on a special paper that acts like blotting paper. The dish contains a small amount of chemical in the form of a liquid that will dissolve the ink. By leaving the paper to stand in the dish, the liquid will gradually soak into it and move upwards. The liquid causes the dyes in the ink to move with it up the paper. As some dyes move faster than others, they'll start to separate from each other, showing the different colours contained in the ink. The patterns that look the same were written in the same ink, but the different patterns in the other samples show that more than one ink was used on the card. Separating ink dyes in this way is called chromatography.
So fractional distillation is used to separate a mixture of two or more liquids that have different boiling points. Chromatography is used to separate very small amounts of two or more coloured dyes. That brings us to the end of this section. Don't forget, there is more information in the series book and on our website.